In this chapter, we're going to look at the physical properties of gases. Uh, Gases are one of the three principal states of matter: solid, liquid, and gas. And understanding these physical properties of gases and the relationships between just various variables helps us understand how gas molecules work and basically how matter in general works. So first of all, gases are pretty common. We've seen them, quite a bit already in lab. We've seen just a lot of elements, non-metallic elements, as well as compounds and mixtures involve gases. Primarily, we've done a lot of reactions in the presence of oxygen, and oxygen is a very reactive gas that's present in air, which is abundant around us. So, again, very, very useful stuff. So, just want to nail down a few terms here as we move on. First of all, I want to distinguish between a gas and a vapor. All right, so as I pointed out, a gas is one of our states of matter, right, as opposed to a solid or a liquid. But typically, when we refer to something as a gas, usually it implies that we're at a regular, an ordinary temperature and pressure, and that's what our material is. It's in the gas state. However, it's possible to get what we call a vapor. Okay, so that's where something's in the gas state, but it is at a temperature and pressure where it's normally a liquid. All right, and so it's or even a solid for that matter, I guess. Yeah, I think especially in the case of things that sublime, like carbon dioxide. But anyway, my point here is that that's the difference between a vapor and a gas in the colloquial sense. All right, so so for example, think of water vapor, where you have water as a gas because you're boiling water, versus water vapor that's just present even at at room temperature. You have water vapor in the air. That's where we get humidity from, and that's that distinction we're going to make here with those two terms. All right, so I mentioned there are lots of compounds and mixtures of gases that we deal with. With the individual elements, remember all of your noble gases are gases, hence the name of that group. And of course, certain diatomic molecules like hydrogen, nitrogen, oxygen, fluorine, and chlorine. So, in this chapter, as I pointed out, we're going to examine some of the properties of gases, and then look at the relationships between those properties. So just to jog your memories, way back in chapter 2, we talked about the differences between solids, liquids, and gases. And I think I pointed out back then that gases are unique in that they don't have a fixed shape nor a fixed volume. Okay, so unlike solids and liquids, which have a definite volume, gases don't. You can compress a gas or you can expand a gas, because you can play around with the space between gas molecules. All right, whereas you can't do that really with solids and liquids. And unlike solids, which have the molecules sort of stuck in roughly fixed positions, liquids and gases are what we call fluids. The molecules are free to move past each other, in any direction. They're not really bound in place like we see in a solid. And again, that's what allows them to have an indefinite shape. Okay, they take up the shape of their container. Okay, now we're going to look at some other properties of gases, the ways to define a sample of gas. And when we look at the relationship between these, we're going to call these gas laws. These are the ways we can mathematically define the relationship between these properties. Okay. Now, before we get to that, all right, we want to sort of understand how gases work. We can define these gas laws simply as mathematical relationships, but to really get meaning out of them, we kind of have to have a working theory behind how gas molecules behave, kind of an understanding or a model to help describe what's going on at the molecular level for those gases. So we call that the kinetic molecular theory. Okay, so basically it's a way to describe the behavior of what's called an ideal gas. Okay, I'll come across that phrase later on. We'll talk about an ideal gas law. But here, just understand that the term ideal gas refers to any gas that follows kinetic molecular theory or any of the gas laws perfectly, okay, as opposed to a real gas. So in real life, there are slight deviations from these from this behavior we're going to see, but don't worry about that for now. I'll come back to that idea in a second. Okay, so what is the kinetic molecular theory? So you want to picture gas molecules. If you kind of zoom in at the molecular level, what do gases look like and how are they behaving? All right. So first of all, gases are made up of tiny particles, either atoms or molecules, depending on what you're dealing with. So if you have a noble gas, obviously, like your particles are atoms. For anything else, you're dealing with molecules, right? And again, if you could have a mixture of gases, and then your molecules don't even have to be identical. But my point is that you've got these tiny particles that are moving around. The key thing here is that these particles are really, really tiny, and they are far apart from each other, and they are constantly in motion. Okay, now I'm going to go into a little bit more detail about this, but you want to kind of get that picture in your head. Okay, so because these particles are so tiny and the space between them is so large, we can basically consider a gas as being mostly empty space. All right, we actually kind of treat the volume of a gas as being basically a measure of the empty space between gas molecules. We kind of treat the gas molecules as, themselves as having like pretty much no volume. Okay. Also, another factor that comes into play here, because these gas molecules are so far apart from each other, is that basically they don't really interact with each other. Then there isn't any attraction or repulsion between these gas molecules. All right, so even if they do collide, they kind of just bounce off each other, and that's that. They don't like stick to each other or anything like that. I mentioned that the molecules are constantly moving. The speed at which this happens is tied into the average kinetic energy of the molecule, which, if you recall back from chapter 2, this is tied into the temperature. So when the temperature increases, your molecule's average kinetic energy also increases, and your gas molecules move faster. Okay, and vice versa. If you lower your temperature and therefore lower your kinetic energy, the gas molecules slow down. Okay, this will continue on up till 0 Kelvin, or absolute zero. At this temperature, your gas molecules have no more kinetic energy and they would stop moving. Okay, so when I said that you want to picture your gas molecules are constantly in motion, the caveat there is that as long as you're at a temperature above absolute zero, which in most cases you probably are, but just so you're aware, this is dependent on the Kelvin scale. All right, so you'll notice that quite a bit in the calculations we're going to do later on. All of our temperatures are going to be in Kelvin. Okay, so something to keep in mind. So yeah, so basically, like I said, you kind of picture your gas molecules the way they are in that picture on the right. They're moving around in straight lines, but of course they're bouncing off the walls of the container, bouncing off each other. They're constantly in motion. These collisions with the walls, we're going to get into that in a second, but that's essentially where gas pressure comes from. Okay, so I'll explain that in a little bit. Now, before I move on, I want to just point out that difference between an ideal gas and a real gas. Right? I mentioned that ideal gases follow these rules, or follow this, or behave according to this description perfectly, right? Gases in real life don't actually do this perfectly. There's slight deviations from this because we make a couple of assumptions here that we've noticed. So, for example, if I go back to the previous slide, I mentioned that we treat gases as being mostly empty space. So when we measure the volume of a gas, we're really measuring the empty space between the molecules. We're not really taking into account the volume that the molecules themselves take up. Obviously, in real life, like molecules take up space, right? But again, this is such a small, minuscule contribution that we can kind of ignore it. It makes the math a lot simpler when we're doing our calculations. But that being said, if you really want to get into the details, you would want to take this into account. This contribution. So again, if you're going to, let's say, chemical engineering or something like that, you want to really sort of pay attention to that, and that's where you would be more interested in how real gases behave. But as far as this class goes, you can assume that all gases behave ideally, okay? Because again, for the most part they do, and like I said, it makes the math a lot easier to deal with in this class. The other assumption we make is that of intermolecular forces. I mentioned that we assume that there are no attractive or repulsive forces between the molecules. Again, in reality, yeah, there are. We learned about intermolecular forces a few chapters ago, and those are a thing. It's just that, again, because your gas molecules are so far apart, the extent of these intermolecular forces are kind of weak. And again, we're kind of safe ignoring them for the most part. Okay, it makes the math a little bit easier. So if you go on to any other forms of chemistry, higher levels of chemistry, you may have to take into account the behavior of real gases, and there are slight modifications into some of the laws we're going to get into that would help you do those calculations properly for a real gas. Don't stress about it for this class. For this class, assume that every gas is behaving ideally. Okay? Alrighty. So, I mentioned earlier there are some properties we're going to pay attention to, and we're going to describe the relationships between them in these gas laws. These properties are pressure, volume, temperature, and the number of moles of gas. And they're represented with a capital P, capital V, capital T, and lowercase n respectively. So let's take a second and look at each of these terms. Pressure, I mentioned earlier just very briefly, that pressure arises from the collisions of your gas molecules with the walls of the container. Right? So what is that? Why does that cause a pressure? For those of you who've taken physics before, you may have seen the formula that pressure is force divided by area, force per unit area. Okay, that's why, generally speaking, if you decrease the area of something, you experience more pressure. So for example, if you push on a balloon with your hand, with your open palm, it might not burst the balloon, but if you poke it with a pin, which is very sharp because it's pointy, that would very easily, break the balloon, or create a hole in the balloon and cause it to burst. Again, that's just a silly example there, but basically that's what pressure comes down to. It's force per unit area. So how do gases exert a pressure? Well, remember, those gas molecules are moving around as long as you're a temperature above absolute zero. Those gas molecules are hitting the walls of the container. Well, when they hit the walls of the container, they're impacting a force on on those containers. With each collision, they're hitting the walls, and they're hitting it with some force. Well, that force per unit area of container wall is your pressure. Okay, so essentially the things that affect this are your numbers of collisions and how strong those collisions are. So generally speaking, if your gas molecules are moving really fast, they're going to hit the walls of the container harder and therefore increase the pressure that way. But I'm getting ahead of myself a little bit. We'll talk about that in more detail when we look at the gas laws. So how do we measure pressure? The first device used to measure pressure, specifically air pressure, it's called a barometer. So it's simply just a glass tube sticking up in a pool of mercury. I'll show a picture of it on the next slide. But you'll see that basically the air pressure exerted on your pool of mercury forces the mercury up the tube, and the height of the mercury column in the tube tells you the pressure. Well, that's why one of our earliest units for pressure is millimeters of mercury, or mmHg, right? Because it's literally the height of that mercury column in millimeters. Now, the simpler unit for that is the torr. So you may see me use millimeters of mercury and torr interchangeably because they're essentially the same thing. 1 millimeter of mercury is equal to 1 torr. Other common units you might see include the atmosphere. Atmospheres, abbreviated as ATM, represents atmospheric pressure, or at least the scale of atmospheric pressure. So 1 atmosphere is essentially air pressure at sea level on a calm day. Okay, that's roughly what 1 atmosphere is. Okay, so it's defined as 760 torr, 760 millimeters of mercury. But that's, that's essentially, if you want to get a feel for what 1 atmosphere feels like, that's kind of what it is, right? So by the way, don't worry about those conversion factors, that 1 atmosphere is equal to 760 torr. We might do a few of these conversions in this lecture. We'll do some example problems, and some of those will involve converting between atmospheres and torr. But if you ever have a quiz or exam, you don't have to memorize that conversion factor. It'll be provided to you if you need it. Okay. There are other units of pressure out there. Another common one is the Pascal. So 1 atmosphere is 101.325 kilopascals. Okay. Another common unit of pressure that you've probably seen when you're pumping up your tires on your car are PSI, or pounds per square inch. So that's another common unit of pressure you've probably encountered. All right. So here's a picture of that barometer I was talking about. So you can see that as you push down on that pool of mercury, and keep in mind your air is made up of gas molecules, right? You've got lots of molecules of nitrogen, quite a few of oxygen, and then a few other gases. They're also moving around and colliding with surfaces, and so they're going to exert a pressure on this surface of this pool of mercury, and they force that mercury up this glass tube. Okay, the tube itself is, basically you have to submerge it completely in the mercury to start off with. You don't want any air or anything inside this because that might interfere with your height of your mercury. But basically, once you stand up the tube, the mercury height will give you an indicator of how much air pressure is pushing on your pool of mercury. So if the pressure increases, that pushes more mercury up into the tube, and so your column, your height of mercury will be higher. Okay, the reason that we use barometers for I'd say probably the most common use of barometers comes from meteorology. So basically weather prediction. Typically air pressure drops when a cold front is coming in, when a storm front is on its way. So if if you're observing your air pressure and you see it starting to drop, that tells you that a storm might be on the way. Okay, so from a kinetic molecular theory standpoint, of course, essentially when it comes to pressure, think of pressure as a measure of the collisions that your gas molecules are undergoing. Either the frequency of those collisions, how many are happening in a given amount of time, or the strength of those collisions. What's the, how forceful are they? How hard are those molecules hitting the walls of the container? Okay. A quick note here about atmospheric pressure before we move on. I already pointed out that we can use atmospheric pressure to detect changes in weather patterns, right? So if you look at a pressure map, oftentimes during your weather report, they'll show you lines, depicting regions of high and low pressure, because that tells you something about the weather that's on its way. All right. The other thing to note about atmospheric pressure is it changes based on your altitude. All right. That's because gravity changes based on your altitude. As you get closer to the center of the Earth, you feel more gravity. right? Gravity is the force of gravity increases as you decrease the distance between the centers of mass of two objects. So as you get closer to the center of the Earth, gravity increases, and conversely, as you get further away from the center of the Earth, gravity decreases. All right, so if you get to the top of a really tall mountain, gravity is acting on you much lower than if you were at sea level or in a valley, right? That's why, of course, then if you're an astronaut, you go into outer space, you're weightless because now you're no longer feeling the gravity of the Earth, right? Well, this also affects air, right? So as you go up a mountain, the air pressure decreases because the air molecules are being compacted less together. Gravity's not forcing them together as much, and therefore the air pressure drops. Okay, so we say that the air is thinner, so to speak, but that's really what it's telling us, is that the air pressure is lower. Okay, next up we have volume. Volume, I think, is pretty straightforward. We've kind of talked about that, and we've measured that several times throughout this semester. But and you've probably noticed that the SI units, or sorry, the metric units that you're going to use here are milliliters and liters. Okay, those are the most common units. Typically, when it comes to gases, since the volume of a gas is variable, the easiest way to figure out what the volume of your gas is to look at what container it's in. That typically tells you what the volume is. All right, temperature. I mentioned earlier that temperature tells us the average kinetic energy of our gas molecules. Again, please note you want to measure this in Kelvin, right? And also keep in mind, of course, when we talk about kinetic energy, we're essentially talking about the speed of the molecules, the velocity. How fast are they moving? So the higher the temperature, the faster your molecules are moving, and vice versa. When you cool down a sample of gas, those molecules slow down. Okay. One common mistake a lot of students make in this chapter is forgetting to convert temperatures to Kelvin. So that's something to watch out for. That's oftentimes where they sort of catch you on a lot of these problems. They'll give you the temperature in Celsius, but you have to convert it to Kelvin for the math to make sense. The reason for this, of course, is that the Kelvin scale, the conversion factor for Kelvin, from Celsius to Kelvin, it isn't multiplied, it's added. And this is what kind of throws the math off. Okay, so when you're multiplying and dividing conversion factors, usually it doesn't matter what units you're dealing with, because your conversion factors also themselves get canceled out when you multiply or divide. But since the conversion to Kelvin is added, you're not really taking care of that if you have 2 Celsius temperatures. All right. So anyway, bottom line, use Kelvin everywhere in this chapter. Basically, never use Celsius. Pretty much always convert to Kelvin. Okay. Occasionally, you might need to give an answer in Celsius. So even if the question's given to you in Celsius, you actually have to convert to Kelvin, do the problem, and then take your answer and convert it back into Celsius. Anyway, we'll practice that later on. We'll see that in more detail. But I just want to really hammer this home, because this is probably, I'd say, the most common mistake you see students making on quiz questions. All right. When it comes to amounts of gases, you can weigh gases. If you have a container, and you add or remove gas from that container, its mass will change. So it's possible to weigh gases that way. But that being said, remember, mass itself isn't as useful to chemists. We really like working in moles, as you've seen in the last chapter. So once you know the identity of a gas, you can use its molar mass to convert from grams to moles. And keep in mind, we can do this backwards as well. If we know the moles of gas from some calculation, we can figure out how much it would weigh using its molar mass. All right, so the same molar calculations we saw in the last chapter, those are going to come in handy here as well. Okay, so make sure you have a periodic table handy when you're doing some of these problems. Okay, With that being said, let's get into the individual gas laws. Now, the first of these is Boyle's law, and Boyle's law is kind of interesting. It's one of the first real scientific discoveries when science was becoming more, more modern, more like science as we know it, and we were getting more systematic at it. Robert Boyle was basically one of the first scientists to kind of study things in this very systematic way that we still use today. Right, so he basically studied gases and saw the relationship between the pressure and volume of a sample of gas. How when he changed one, how did the other also change? Right, so what he noticed was that there was an inverse relationship between the two. When the pressure of a gas increased, the volume decreased, and vice versa. If you increased a volume, the pressure decreased. All right, so basically these two have an inverse relationship, or they're inversely proportional. Okay, now caveat here, you've got to have this under controlled conditions. So while you're observing pressure and volume, you have to make sure those are the only two things that are changing. So that means for your sample of gas, you have to keep the amount of gas, and therefore the moles, constant, and you also have to keep the temperature constant. All right. When you change the volume of a gas, sometimes the temperature will change as well. So you have to change the volume relatively slowly to allow the system to not be affected by these temperature changes. Okay. So from a kinetic molecular theory standpoint, why is this the case? Why does changing the volume change the pressure? Well, imagine you have a sample of gas and you decrease its volume. All right, so you're sort of squeezing the sample of gas. You're moving the walls of the container closer together. Okay, now that means there's less space between the molecules. So what's going to happen to the number of collisions? All right, so here's a picture to help you see that, right? So you start off with a sample of gas, and you push down on this piston here to decrease the volume. And in doing so, you're kind of forcing the molecules closer together, so the amount of empty space is smaller. There's less empty space there. What's going to happen to our number of collisions? Well, our temperature hasn't changed, so these gas molecules are still moving at the same speed. They're going to collide with the walls of the container more often. And when they do that, well, remember, the more collisions, the higher the pressure. Okay, so notice that decreasing the volume increased the pressure. Right? So we say that's an inverse relationship, or they're inversely proportional. Moreover, notice the numbers here in this example, right? Notice that we took our volume from 4 down to 2, right? We halved our volume. Notice that our pressure doubled from 1 to 2. Okay, so that again shows that inverse relationship. So if you wanted to write that out as a mathematical relationship or an equation, well, you could say that the pressure is proportional to the inverse of volume, which, by the way, this is the proportional symbol. Okay, that just shows there's a relationship between these two terms. And because these are inversely proportional, we write the 1 over volume. That's the inverse of volume. Okay, so the way we describe this is we'd say that pressure times volume is equal to some constant. So we can see here 4 times 1 is 4, just as 2 times 2 is 4, right? So our constant here is 4. So another way you could write this law out, and this is probably the more common way you'll see it written, is that your pressure times your volume initially, your initial pressure, P1, and your initial volume, V1, multiplied by each other, is equal to your final pressure, P2, times your final volume, V2. Again, 4 times 1 is equal to 2 times 2. Okay, they're both equal to 4. The next law we're going to learn shows the relationship between temperature and volume. This is called Charles's law. All right, so Charles' law shows the relationship between temperature and volume, and essentially these two are going to be directly proportional. So if you increase the temperature of a gas, if you heat it up, its volume will increase to match, and vice versa. Okay, so this is a direct relationship, or we say they are directly proportional to each other. All right. Now, again, please note that you need your temperature in Kelvin for this to work. All right. And also, of course, just like with our Boyle's law, we want to only change the two variables that we're varying, right? We want to compare volume and temperature, but that means we have to keep the pressure and number of moles constant. Okay, so you have to allow, your sample of gas to sort of equilibrate with the atmospheric pressure around it. So oftentimes we show Charles' law using balloons, right? It's usually a good device to do this because the thin, flexible rubber skin of a balloon will allow the pressure inside the balloon to equal the atmospheric pressure around it. Okay, so why do we see this directly proportional relationship? Right? So think about what the gas molecules are doing. So, for example, if you are, let's say you are increasing the temperature, right? Well, the molecules start moving around more, right? They start moving faster. They start hitting the walls of the container more. Now, this would cause an increase of pressure. So to keep the pressure constant, the balloon has to give, your sample of gas has to take up more room. Okay, so it's kind of like, in order for, because you're allowing the pressure to stay constant, because your container is kind of flexible in this sense, the increase of that force inside your sample is sort of pushing against the walls of your container and increasing its volume. Okay, and it'll keep on doing that until the pressures stay constant, and so basically that increase in temperature will cause an increase in volume. And of course, the opposite happens too with decreasing your temperature. You have less of a push against the atmosphere around your sample, and that causes your volume to decrease. Okay, so if you want to visualize it, here's so again, we're going to see volume is directly proportional to temperature. Okay, so that means if one increases, the other one increases. If one decreases, the other decreases. So here we can see we have a sample, at 200 Kelvin, and we have a volume of 1 liter. We're going to double that temperature to 400 Kelvin, right? So these molecules are moving around twice as fast, and they're going to push against that piston and cause it to expand to twice the volume. So the volume goes from 1 liter to 2 liters. Okay, and now at this point, the number of collisions here will be the same as the number of collisions here, so the pressure stays constant. But the only way this is possible is if that volume doubles. Okay, so how are we going to mathematically describe that, right? We know that volume here is equal to some constant times temperature. Okay, in this case, that constant is 200, right? 1 times 200 is equal to 200. 2 times 200 is equal to 400. So again, if you want to write this out, as a relationship, the way you often see Charles' law written is V1 over T1 is equal to V2 over T2. So your initial volume divided by your initial temperature will equal your final volume divided by your final temperature. 1 divided by 200 is going to be the same as 2 divided by 400. Now again, notice that we used our temperature in Kelvin. Okay, and I've mentioned this before, but I can't stress enough, this is very, very important. If you don't use Kelvin, you don't see that directly proportional relationship. I mean, they are proportional, but it's not going to be that nice linear relationship that we see. It's linear, but everything's kind of shifted over. Okay, by 273 degrees. So you want to be careful with that. Okay. Okay, the last relationship we have here is Gay-Lussac's law. All right, so here we've got the relationship between pressure and temperature. So again, we're looking just at pressure and temperature, which means we've got to keep volume and our amount of gas constant. Okay, so what's the relationship in Gay-Lussac's law? Well, it turns out they are directly proportional. Okay, your pressure of your sample of gas will increase when your temperature increases, and vice versa. If you cool down your sample of gas, the pressure will drop. Okay, and this kind of makes sense, right? Basically, if you have your increase your temperature, your molecules are moving around faster. Well, if you're keeping your volume constant, what's going to happen to your number of collisions? Well, they're going to hit the walls of the container more often, and therefore your pressure will increase. By the way, this is why aerosol cans and anything with gas inside them have those warning signs not to leave them in direct sunlight or throw them into an open flame or anything like that. Any residual gas that's trapped inside your container, because it's trapped inside a container that has a fixed volume, could theoretically keep on having its pressure increase until the can ruptures, right? That's basically how bombs work. Okay, so essentially, you want, if you have a sample of gas that expands rapidly to the point where it causes the container to burst, and those fragments of container are sharp and therefore dangerous. That's what shrapnel is. That's basically the principle behind every explosive device. Okay, and that's why anything with a gas trapped in it has that warning sign, that warning label. Okay, so basically, again, as I pointed out, you increase your temperature, you're increasing the speed at which the molecules are moving around, and therefore since they have the same amount of space to move around in, you're going to increase the number of collisions. All right, so we say that pressure is directly proportional to temperature, so pressure divided by temperature is some constant, and therefore P1 over T1 is equal to P2 over T2. Okay, so it's kind of similar to Charles's law, because their volume and temperature are also directly proportional, though, of course, here we're dealing with pressure, not volume. Okay, before we move on, quick note here about vapor pressure. I've talked about vapors before. That's where we have, a solid or a liquid giving off gas molecules, right? And we call those gas molecules vapor. Well, the presence of a vapor basically causes its own pressure, right? So you can get a measure of how much of your sample of solid or liquid is vaporizing by measuring this pressure. Okay, this is effectively like how they measure humidity, by the way. So like your amount of water that's being sent into the atmosphere, that's essentially a measure of humidity. So on a very humid day, it just means that you have more water vapor in the air. All right. So a little note here about vapor pressure and its relationship to boiling point. So again, while you have molecules escaping as a gas, okay, and that's what vapor is, you simultaneously have some of those gas molecules condensing back into a liquid or solid, right? In the example I have here, a liquid. So basically, you have this equilibrium. When that vapor pressure is equal to the atmospheric pressure, that tells you that you're at your boiling point. Okay, you're essentially, that's where you're going to have that equilibrium between a liquid and a gas, which is what we call boiling or condensing, depending on whether you're heating it up or cooling it. This is why you have a lower boiling point for liquids when you are at a place that has a lower atmospheric pressure. So if you go up in altitude, if you go up a mountain, or even here in the Adirondacks, for example, where we are above sea level, you'll notice a drop in boiling points for liquid. So I don't know if you recalled back in lab 2 that we had a slightly, we observed the boiling point of water and we saw it's a little bit below 100 degrees Celsius. And that's okay. That's kind of normal up here because our atmospheric pressure is less than the atmospheric pressure at sea level. Okay, what we call the normal boiling point of water is 100 degrees Celsius. When you have a lower atmospheric pressure, this boiling point drops, right? You reach that equilibrium at a different temperature. But this, by the way, is why you might notice certain food items have what are called high altitude directions. So if you're, climbing up a mountain, or you live in a mountainous town where you're at a lower atmospheric pressure, typically when you cook food, you're relying on water boiling to provide the heat necessary to cook the food. Well, if your water is going to boil at a temperature below 100 degrees Celsius, it's not going to cook the food as well. So you oftentimes these high altitude directions involve you using more water and heating for a longer period of time to fully cook the food. Right. Conversely, before I forget, just want to tie together how vapor pressure is related to temperature. Basically, please note that the vapor pressure will, of course, increase with an increase in temperature. It makes sense that if you increase the temperature, you have more, you have a higher average kinetic energy for your molecules, and therefore you'll have more molecules that meet that threshold for escaping as a gas. All right, so regardless of what temperature you're at, you're always going to have a few molecules that are capable of escaping as a gas. That's why you have vapor pressure pretty much always. It's why, for example, if you leave a glass of water open at room temperature, it'll eventually evaporate because the top of that glass of water is not closed, and so those gas molecules escape, and you constantly keep on losing gas molecules that way. But generally speaking, if you increase the temperature, your vapor pressure should go up. Okay, this is why it tends to get more humid on hot days, for example. All right, so with these three gas laws that we've learned, Boyle's law, Charles' law, and Gay-Lussac's law, we can kind of smush them together and make what's known as the combined gas law. Each of these individual gas laws compare two variables at a time. If we combine them, we get the combined gas law, as the name suggests, where we can compare all three variables at the same time. Okay? Now, the really neat thing here is that because this is all three laws sort of combined together, we can use this combined gas law to kind of figure out any of the individual gas laws. So you actually don't have to memorize your individual gas laws. This combined gas law is provided to you on any quiz or exam. It's usually on your formula sheet. And you can use this to solve pretty much any problem where you have a change in pressure, or a change in volume, or a change in temperature, or a change in all three things. Okay, so that's why it's P1 V1 over T1 versus P2 V2 and T2, right? Your pressure is changing from P1 to P2, your volume's changing, and so on. Okay, so if you know, out of these 6 variables, if you know 5 of them, you can solve for the missing 6th. In the case of the individual gas laws, of course, though, we are keeping 2 of these variables constant, and so they kind of drop out of the equation because they're going to be the same number and they cancel each other out. Let me give you an example here. For example, let's say our temperature is constant. So if T1 and T2 are the same number, well, you're dividing by the same number on both sides, so they just cancel out, and you're left with P1 V1 is equal to P2 V2. Well, that's Boyle's law, where you've got to keep temperature constant anyway. So again, that's, if you are ever trying to solve a problem that changes only 2 of these variables instead of all 3, know that you can do that just by canceling out the necessary variables. We'll do some practice problems in this later on, so you'll see what I mean later on in this lecture video. Okay, so you notice that we haven't talked about moles much so far. So let's talk a little bit about the relationship between our gas law variables, pressure, volume, and temperature, with moles, right? Specifically, what we label as N in our gas laws. All right. Now, the name Avogadro probably rings a bell. If you remember in the last chapter, we learned about Avogadro's number, and it was the number of particles in a mole, and it was named after Amedeo Avogadro, the scientist who discovered that relationship. Well, the he was able to figure all this stuff out by doing experiments on gases. So it's actually stuff from this chapter that led to some of the discoveries in the previous chapter. All right. So basically, he noticed that the amount of gas was tied into the volume. If you change the, your increased your sample of, your sample of gas, the number of molecules or moles of gas, your volume would change directly proportionally with that. Okay. So if you want an example of Avogadro's law that you want to see in real life, just picture blowing a balloon, right? When you're blowing up a balloon, the pressure is going to stay constant, right? The pressure inside the balloon will equal the air pressure outside of it. You're injecting more gas into the balloon, right? You're blowing carbon dioxide into the balloon, and it's going to, as the moles of carbon dioxide go up, your volume is also going to grow up, right? As your balloon expands. Okay, so, and of course we keep pressure and temperature constant there, right? Your atmospheric pressure is equal to the pressure inside the balloon, and typically your temperature of your balloon is going to be roughly about the temperature of the atmosphere around it. Okay, so again, if you want to see this sort of visualize, here we've taken a sample of gas, and assuming we're keeping pressure and temperature constant, if we double the amount of gas, notice that the volume also doubles. Okay, so if you want to express that mathematically, volume is directly proportional to number of moles, and therefore volume is equal to some constant times the number of moles, which means V1 over N1 is equal to V2 over N2. Okay, so just like with the combined gas law, if we take all of our individual laws, including Avogadro's law, we can kind of smush them together and see how they're all related. Okay, so if we take Boyle's law, where volume is inversely proportional to pressure, we take Charles's law, where volume is directly proportional to temperature, and we take Avogadro's law, where volume is directly proportional to number of moles, we've essentially said that volume is equal to our temperature times moles over pressure, with some constant in mind. So I've kind of used the same constant here, K. Again, I'm just using a generic constant. The constant itself isn't important here. But this shows the relationship between temperature, number of moles, and pressure with volume. Okay, I kind of picked the same variable and just redefined everything with volume on one side there. Now, typically, we rearrange this so that everything's on one line. It just makes manipulating the equation a little bit easier. So to do that, we're going to multiply by pressure and move it to this side. Okay. We're also going to give our constant here a special symbol, and that's going to be R. So our pressure times our volume is equal to our number of moles times our constant R times our temperature. Okay. So that combines all of these gas laws together. Instead of the combined gas law, where we have two sets of variables, pressure, volume, or temperature, here we've got one of everything, but we have a constant and number of moles mentioned. Okay, whereas with the combined gas law, your number of moles are staying constant, right? You have a fixed sample, but you're just changing its pressure, volume, and or temperature. Okay, here your pressure, volume, moles, and temperature are all staying constant, but this shows the relationship between them. Now, what is R, right? R is what's called the gas law constant. Now, be careful if you're given a generic chemistry formula sheet. Basically, there are multiple versions of R depending on what you're using. You, for example, might see that if you just Googled R, you might get 8.314 joules per mole Kelvin. Don't use this number. This number is tied into a lot of thermodynamics calculations, things that you would probably see more in Chem 111, 112. We're not going to use this number over here in this class. The more important number for you is this other definition of R, which is 0.0821 liter atmospheres per mole Kelvin. All right. Now, those units are kind of a mouthful, but that's because we're tying together pressure, volume, moles, and temperature, right? And so in order to show that, to get all of our units to cancel out, we have to define our units for that constant to make sense. So in other words, our pressure must be measured in atmospheres, our volume must be in liters, our moles must be in moles, and our temperature must be in Kelvin. Okay, in order for this constant to be 0.0821. If you have any different units for these, for any of these four variables, this number would be different. Okay, so be aware of that. There might be other versions of R out there where this number is different, but that's because these units are different. So you want to be careful, with the units we're using in our question with the units in R. All right, and again, don't worry, we'll do some practice problems here, so you'll see what I mean by that. Okay, quick point here I want to make with the ideal gas law and the individual gas laws. Just like our combined gas law, which can give us any of the individual gas laws by taking out any variable that's kept constant, with the ideal gas law, you can rearrange it to give any of the other individual gas laws. So for example, in Boyle's law, we keep the temperature and number of moles constant, right? Well, if you take the ideal gas law, PV is equal to nRT, what you're essentially saying is that nR and T are constant. So that means your pressure times volume is what's changing. So in other words, your pressure times volume before is equal to your pressure times your volume afterwards, because nR and T are constant. So you can kind of derive your individual gas laws from your ideal gas law. Not that any of you ever have to do that. The ideal gas law is provided to you, the combined gas law is provided to you. This is just kind of showing this algebraically for people who like to see that sort of thing. Okay, so you can see that's where we get Boyle's law. That's one way you can derive it. Okay, you can do this with any of the other laws too. Charles' law, of course, you keep moles and pressure constant, and with Avogadro's law, you're keeping your temperature and pressure constant. Okay, so one of the neat things about the ideal gas law is that when you have a sample of gas, you can, of course, solve for any variable, but what's really neat is if you have what are called standard conditions. Okay, if you're at standard temperature and pressure, often abbreviated as STP, we say that our temperature is 0 degrees Celsius, right? That's 273 Kelvin, and our pressure is 1 atmosphere. Well, if that's the case, if those are standard conditions, then we are essentially going to relate together our volume and our number of moles, right? Those are our only variables there because R is also a constant. Okay, so the nice thing here is that we can then figure out that our volume, if we plug in our pressure as 1 atmosphere and our temperature as 273 Kelvin into our formula PV is equal to nRT, we'll see that for 1 mole of gas, where n is equal to 1, our volume is 22.4 liters. So now here's a really neat thing about this. Notice that I said that, I kind of just referred to our gas. I didn't say what type of gas we have. And that's the really neat thing. It doesn't matter. This applies to any gas out there. If you have 1 mole of gas at standard temperature and pressure, you have 22.4 liters of that gas. That's the volume it will take up. It doesn't matter what the gas is. Okay, so notice here we have 3 balloons. We have 1 mole of helium, 1 mole of oxygen, and 1 mole of nitrogen. They all take up a volume of 22.4 liters. Okay, But now, remember, elements don't have the same molar masses. So 1 mole of helium weighs 4 grams, because helium's 4 grams per mole. You can look this up in your periodic table. Oxygen molecules weigh 32 grams per mole, so this balloon would weigh 32 grams. And nitrogen would weigh 28 grams, okay? Because nitrogen molecules have the molar mass 28 grams per mole. Okay, so that's the difference in mass, but the volume is constant for all three. Okay, something to keep in mind then, that this also then affects the density of gases. If they keep the volume constant, but the mass changes, remember, density is that relationship between mass and volume. Okay, so generally speaking, the heavier the gas, the denser it's going to be. Okay, assuming you're keeping all your samples of gas at the same conditions. This, by the way, is we can take advantage of this in a bunch of different avenues. For example, carbon dioxide is used in fire extinguishers because it is denser than the nitrogen and oxygen in the air around it. So it'll tend to sink to the bottom and sort of cover anything that's on fire and stop oxygen getting to it. Okay, helium is used for balloons because helium is going to be lighter than nitrogen and oxygen, and therefore it's going to be less dense than air, and this is why a helium balloon floats. Okay, this also, by the way, is why hot air balloons float in just regular air, because as the air heats up, it expands, and that decreases the density of your hot air balloon. That's what causes it to float there. Okay. So now notice that the neat thing here with our ideal gas law as compared to our combined gas law is the presence of that number of moles. I pointed out that in the last chapter, moles are very, very important to chemists. We love measuring things in moles because it's a great way to count out amounts of things, all right? So you'll notice, just like in the last chapter, moles are going to be very useful in this chapter and, the next few to follow, because they're really going to help us with telling us the amounts of things. And this is no different with gases. We often want to know how much gas, how many gas molecules or moles of gas do we have in a sample of gas? Can we do stoichiometry with that? And the answer is yes. The nice thing here, though, is that it's the same principles we learned in the last chapter. When you want to get from moles of chemical A to moles of chemical B, we're just going to use a molar ratio like we saw in the last chapter. But we saw that we're not often given moles or asked for moles. Oftentimes, we might be given grams, or we might be asked for an answer in grams. Okay, so in order to get from grams of chemical A to grams of chemical B, we have to get through moles. We convert we go to moles of A, we do our molar ratio, and then we get out of moles. The same thing can apply, okay, to our gases, except now, instead of getting to grams using our molar mass, we're going to get pressure and volume using our ideal gas law. Okay, because if we have, 4 out of these 5 things, well, we're going to find the missing one. And the thing is, we can relate, our pressure, volume, constant, and temperature to our number of moles. The moles, N, is essentially the same thing that we're using in our molar ratio, right? So if you have the information about gas A, you can figure out moles of gas A by solving for N. Likewise, if you have N, once you've done your molar ratio, for chemical B, your moles of chemical B, you can then convert it to a pressure or volume or whatever using the ideal gas law. Okay, and again, we're going to get into some practice problems on that in just a little bit. But basically, the key thing here with any of these types of problems we're about to get into is you want to know what formula to use, and you need to be able to algebraically manipulate it so that you have just the variable you want on one side. We've kind of done this already in previous chapters. I believe we did this with the with the specific heat formula, Q is equal to mc delta T. It's the same concept. You're just rearranging your formula to solve for what you want. Okay, and this applies to any to the combined gas law as well, right? And that's where we're going to kind of practice. So here's an example. So let's say we have a sample of gas. We know its pressure, we know its number of moles, we know its temperature, and we want to find out its volume. All right. Well, first of all, we want to use the ideal gas law here. Notice that the question only gave us one pressure, one number of moles, one temperature, and it was asking us for one volume. We're not changing any pressure, volume, or temperature. Now, I want to use my ideal gas law here, and I want to solve for volume. So how do I get volume by itself on the left-hand side of the equation? Well, I need to move pressure to the other side. So remember, to move things in an equation to the opposite side, you've got to do the opposite of whatever operator is on here. So if we see pressure times volume, right? There's no operator, so it's understood that we're multiplying these two things. The opposite of multiplication is division. So I'm going to divide by P to get my volume. Okay, volume is equal to nRT divided by P. Okay, and that the question will give us each of these variables, or if not directly, it'll give us some way of finding one of these variables, and we just plug them into this formula and plug those numbers into our calculator and write out that answer. Okay. Again, we'll notice that if we set this up correctly, all the units of R will cancel out. So that's another indicator that we've done this correctly. N, T, and P, those units will cancel out in R's units and leave behind only liters. Our volume will be in liters. Okay, we could do this with the combined gas law as well, of course. This gets a little bit tougher because this is written out as a fraction. And oftentimes, I think this is going to be the other really common mistake students make. When you're solving for one of the things in the denominator, there's a common algebra mistake you've got to watch out for. So I'd recommend, first of all, pause this video, try solving for T1, and see if you can do this by yourself. Okay, and then hit play, and we're going to show you the answer. Okay, so you should have gotten P1V1 times T2 over P2V2 to equal T1. Some of you may have gotten the inverse of this. You may have gotten P2V2 divided by P1V1 over T1 times T1, times T2. The reason for this is, like I said, a common algebra mistake. You didn't solve for T1, you actually solved for the inverse of T1. You've got to be careful here because T1's on your denominator. All right? So a quick way to avoid this problem, this common pitfall for a lot of students, is to start off and just get everything on one line. So my advice is actually to start off just cross-multiplying your temperatures up here. Okay, so we're going to move, so basically if we multiply T1 to the opposite side and multiply T2 to the opposite side, we get P1 V1 T2 is equal to P2 V2 T1. Okay, now notice that everything is on one line, just like in the ideal gas law, and this makes manipulating this equation much, much easier. Remember, we wanted T1 by itself, right? Well, you divide by P2 and divide by V2, and that's how we get the equation that we want. Okay, whereas a lot of people just automatically send P1 and V1 to the opposite side, and what they don't realize is that T1 isn't by itself. Dividing by P1 and V1 doesn't make this nothing, it makes this a 1. So you actually wind up getting 1 over T1. Okay, so something to watch out for when you're manipulating these, the combined gas law. Okay, so let's try some practice problems involving the ideal gas law, involving the combined gas law, and see how do we apply these to solve problems.
So when you get a paragraph problem like this, as always, you want to keep an eye out for the useful information. What I usually do is I look at the numbers in the question and I just underline them and their units. Okay, so at least that way I start getting a feel for what variables the question's giving me. And of course, please make a note of what the question's asking you for. Okay, so if I'm reading this question, I'm saying, all right, a balloon is filled with 1,300 moles of hydrogen. So that's probably something that's important. Okay, if the temperature of the gas is 23 degrees Celsius and the pressure is 750 torr, what is the volume of the balloon? Okay, so the question's asking us for volume. So notice that I've underlined a number of moles, a temperature, a pressure, and I'm being asked for volume. Now, and I only have one of each of these variables. I'm not changing pressure, changing temperature, changing volume. So this should initially let me know I'm probably going to use the ideal gas law. Okay, just from the fact that I've got the four variables that are in the ideal gas law, PV is equal to nRT. Okay, so if you want to visualize this, there's our balloon, and here's the information that the question's given us, and we're being asked for the volume. Right? Now, with your formula PV is equal to nRT, you have to know the value of R, 0.0821 liter atmospheres per mole Kelvin. And again, you don't have to memorize that, but you should have that in front of you to do this problem. But especially notice the units there. Liter atmospheres per mole Kelvin. So we're going to solve for our volume in liters, but in order to do that, we need our pressure in atmospheres, which they're not. We're going to have to convert that to atmospheres. We need our moles in moles, which they already are, so we don't have to do anything there. And we need our temperature in Kelvin. We're going to have to convert our 23 degrees Celsius into a Kelvin temperature. Okay, now to help you with those two conversions, I'll remind you that 1 atmosphere is 760 torr. Okay, again, you don't have to memorize that number, but you're going to have to look up that conversion factor for this problem. And of course, to convert from degrees Celsius to Kelvin, you've got to add 273 to our 23 degrees Celsius. So when we're solving this problem, basically you convert your pressure from 750 torr, you divide by 760 torr per atmosphere, and you get 0.987 atmospheres. Of course, when you add 273 to 23 degrees Celsius, you get 296 Kelvin. And of course, here's our value of R. So when we solve for our volume, okay, we want to rearrange PV is equal to nRT. So to get volume by itself, we divide by pressure. So we have nRT divided by P. So we're just going to plug these numbers into that equation. We're going to take our moles, which is 0.987. We're going to multiply by our moles is 1,300. We're going to multiply by our value of R, 0.0821. That looks like I rounded off to 0.082. And our temperature of 296 Kelvin, we're going to divide by our pressure of 0.987 atmospheres. Okay, so when you plug these numbers in, notice that your units of R cancel out. Moles cancels out with moles, right? Our atmospheres cancel out with atmospheres. Our Kelvin cancels out with Kelvin, and what we're left with is liters. Okay, so this is why the units of R are what they are. But basically the idea is that everything should cancel out, leaving you with the units that you want. So when you plug these numbers in, you take 1300 times 0.0821 times 296, divide by 0.987, you get somewhere in the ballpark of 32,000 liters. Okay, and again, your rounding might be a little different. I think when I made this slide, I used 0.082 instead of 0.0821. Again, it'll be a close enough answer for multiple choice. But basically, you should get something in this ballpark. Okay, let's try a different problem. A 0.105 gram sample of gaseous compounds of some gas has a pressure of 561 torr in a volume of 125 milliliters at 23 degrees Celsius. What's its molar mass? Now, this question's a little bit different. It's actually kind of two problems in one. You're going to have to use do a gas law problem, but then you're going to take that answer and go a step further to find the final answer. So let's see what the question's giving us here, right? It's telling us that the mass of our sample is 0.105 grams. Okay. It has a pressure of 561 torr, a volume of 125 milliliters, and a temperature of 23 degrees Celsius. Now, we're searching for molar mass, which has units of grams per mole, right? Now, we don't know the identity of our compound, so we can't use our periodic table to look up the molar mass. What the question does give us is the grams, which means we could figure out our grams per mole, our molar mass, if we had the moles of the compound we're dealing with. You see, so this is where we're breaking this down to two problems. Okay, so you can take your pressure, volume, and temperature, and you can solve for n, your number of moles, accordingly. Of course, just like the last problem, for this to work, for your ideal gas law to work, your pressure has to be in atmospheres, not torr, and your temperature has to be in Kelvin, not degrees Celsius. Okay. Likewise, your volume has to be in liters, not milliliters. Okay, because those are all the units within the units of R. So to help you out, I've gone ahead and done the conversions if you want to check your work. And so I would use the pressure, temperature, and volume to solve for the number of moles. Once you've got the number of moles, then you can use that mass of 0.105 grams and your number of moles to figure out the molar mass, the final answer, in grams per mole. Okay, so let's walk through that problem together. Okay, but feel free to pause this if you want to try this out yourself first. All right, so when we rearrange PV is equal to nRT, to get n, which is our number of moles by itself, we'd want to divide R and T to the same side as PV. Okay, so in other words, if you've rearranged your formula correctly, you should have PV divided by RT on one side and n, number of moles, alone by itself on the other side. Okay, and that tells you can plug those numbers in this order. Okay, so we're going to take our pressure in atmospheres, our volume in liters, divided by the value of R, and divided by our temperature in Kelvin. Okay, and you'll notice our units cancel out accordingly, and we're left with moles. Okay, so I've written this answer out in scientific notation, but if you wrote this out as a decimal, if you got like somewhere around 0.004, somewhere in that ballpark, that's fine as well. Okay, so we have our moles. To find our molar mass, remember, it's grams per mole. Those are the units of molar mass. And the nice thing here is that even though there isn't a formula to figure out what molar mass is, you can just use those units to do it. We've got our 0.105 grams. We have 0.0379 moles. We just take one and divide by the other, and the units give us grams per mole. And that's the answer. Okay, that's how you would solve this problem. All right, here we have a stoichiometry problem, right? You can tell this is a stoichiometry problem because they're giving you a balanced equation and they're giving you information about one chemical and asking you information about another. Notice this question gives you information about hydrogen. They give you a volume of hydrogen, they give you the temperature, they give you the pressure, and they're asking you about ammonia. Okay, so that alone should tell you that this is a stoichiometry problem. Okay. Now remember, for a stoichiometry problem, you have to have moles of one chemical and you're trying to get to moles of another. But remember, a lot of stoichiometry problems don't start you off with moles. You have to do that first step yourself. And that's the case here. They've given you the volume, the temperature, the pressure. You need to find out the moles of hydrogen yourself using that information. And as you've probably seen in the last two problems, the best way to figure out moles using this other information is to use the ideal gas law. You're solving for n in PV is equal to nRT. All right? And of course, don't forget your volume should be in liters, your pressure should be in atmospheres, which it's not, and your temperature should be in Kelvin, which again, it's not. So make sure you make those necessary conversions. All right? Once you have the moles of hydrogen, of course, then it's a simple molar ratio to get to ammonia. Our balanced equation tells us there are 3 hydrogens for every 2 ammonias, so it's a 2 to 3 ratio. So you can convert that the same way we did in the last chapter. Okay. Now there's a follow-up question here, and it tells you to take that answer in moles. It gives you a volume, it gives you a temperature, and it's asking what's the pressure of that gas. So this is a second separate problem. So first let's focus on this first one. So we're starting off with this tank of hydrogen left with that information. Okay, so we want to take this information and convert that to moles and figure out how many moles of hydrogen we have here, and that will then help us find the moles of ammonia. Okay, and then of course once we have that, we have a new problem where we're trying to figure out the pressure from that information. Okay, so let's try this out. So again, if you haven't already done so, I've converted our pressure into atmospheres here for you. Here's our volume, here's our temperature converted to Kelvin. And let's solve for moles. So take your formula PV is equal to nRT. How do we get N by itself? Okay, so hopefully you would have divided by R and T, and you would have rearranged your formula to the way it looks like that. And then you just plug those numbers in accordingly. All right, we take our pressure in atmospheres times our volume in liters and divide by R and T in Kelvin. All our units should cancel out, leaving just moles. And you should get an answer somewhere in the ballpark of 10.35 moles. Again, maybe not perfectly this number, but somewhere in that ballpark. Okay, so now remember, this is moles of hydrogen. I pointed this out in the last chapter, but whenever you have a stoichiometry problem, I really recommend when you're writing out numbers or units, also include what chemical they belong to. Otherwise, it's easy to get lost between what your different numbers represent. So this is moles of hydrogen, and now we're trying to get to moles of ammonia, and this is where our 2 to 3 ratio is going to come in. Okay. So we want moles of hydrogen to cancel out, so that's why we divide by 3. And we want to be left with moles of ammonia, so we multiply by 2. So we get about 6.9 moles of ammonia. Okay, and that's how we do that problem. Okay, so I'm going to move on here, but I'll put up the answer for that second half. That's just another practice problem if you'd like to try it out yourselves, okay? Okay, so hopefully you got a pressure of 1.35 atmospheres when you try that problem out. Okay, so let's have a look at this problem, which is going to be slightly different from the other ones we've looked at. We might be using our combined gas law, as you can see here. So we have a sample with a pressure of 55 torr and a volume of 125 milliliters. The sample is then compressed so that the new pressure is 78 torr. What is the new volume of the gas? And the question also mentions that the temperature does not change. Okay, so you can see how this is already different from the other problems we've done. Instead of being given one pressure, one volume, one temperature, and being or one number of moles or something equivalent, you're given 2 pressures and 2 volumes. Well, you're not given the second volume, you need to find it out. But my point is here that this tells you that this is a combined gas law problem because there are 2 of the same type of quantity. All right, that should give that away. So if we have a pressure, we're given a pressure of 55 torr, that's our P1. P2 is 78 torr. And our V1 is 125 milliliters. V2 is, well, we don't know what V2 is. That's what the question wants us to find. As for T1 and T2, we're told that they do not change. So T1 and T2 are the same number, which means they drop out of our combined gas law equation. Okay, so just as a summary, here's the numbers that are given to us. Okay, now you're probably saying to yourself, wait a minute, do I need to change my pressure into torr or my volume into liters? The nice thing with the combined gas law is that you don't have to match the units of R because R is not involved in the combined gas law. So as long as your units are the same, they will cancel out. So you can leave your pressures in torr, and that's all right. You can leave your volume in milliliters, just realize that your answer will also be in milliliters. Okay, so be careful if the question wants you to give your answer in something other than milliliters, but the bottom line is the units will stay consistent. Now, the only place where you have to do a conversion, of course, is with temperature. I've pointed out that even if you are given degrees Celsius and you want your answer in degrees Celsius, you have to do the conversion in Kelvin. And that's just the nature of the conversion factors of degrees Celsius to Kelvin. Okay, so let's set up our combined gas law. So I've left out T1 and T2 here because they cancel out. But if this were the combined gas law, basically it'd be P1 V1 over T1 is equal to P2 V2 over T2. But since T1 and T2 cancel each other out because they're the same number, I've left them out here and we're left with just Boyle's law. All right. So now we're solving for V2. So we want to rearrange this so that V2 is by itself. So how would you move P2 to the other side? Well, since it's P2 times V2, the opposite of multiplication is division. So V2 is going to equal P1 V1 divided by P2. Now that you've got your new volume by itself, since that's what you're trying to solve for, just plug your other numbers into the equation. Okay, so we're going to take 55 times 125 divide by 78. Notice that our units of torr, millimeters of mercury, cancel each other out, and we're left with our answer in milliliters. Okay, so you should get somewhere around 88 milliliters. All right, let's try a similar problem. So a balloon is inflated with helium to a volume of 45 liters at room temperature, 25 degrees Celsius. So notice we're being given a volume and a temperature here. If the balloon is cooled to negative 10 degrees Celsius, so we've got a new temperature, what is the new volume of the balloon? So we're being asked for the new volume. We're also told that pressure does not change. So we're going to use the combined gas law here. Again, we've got a changing volume, a changing temperature, but we're told the pressure does not change, which means that P1 and P2 are the same number, and therefore they cancel each other out. So they're not going to show up in our combined gas law problem. And so what we're left with is Charles' law. V1 over T1 is equal to V2 over T2. Okay. Now, again, this is one of those combined gas law problems where you do have to convert your temperature into Kelvin. Okay, so this is what I was kind of warning you about. Even though both these units are degrees Celsius, they actually won't cancel each other properly. If you try doing this in Kelvin, you'll get a different answer than if you left these in degrees Celsius. Okay, and so in order for this to work, you have to convert your temperatures into Kelvin first. Okay, so instead of using 25 degrees Celsius for T1, we're going to use 298 Kelvin. Likewise, negative 10 degrees Celsius is 263 Kelvin. All right, so make sure you use that number. Right away, you can tell that if you had left these numbers in degrees Celsius, you would get a really weird answer because since T2 is a negative number in degrees Celsius, you would have got a negative answer eventually for your volume, and that doesn't make any sense, right? You can't have a negative volume. So that alone should remind you that changing into Kelvin is very, very important. But even if T2 were a positive number, you still have to do this in Kelvin. Okay, so let's write out our combined gas law. I've left out P1 and P2, because they cancel each other out. So what we're left with is effectively Charles' law. Now we're solving for V2, so how do we move T2 to the opposite side? Well, since we're dividing by T2, we would multiply it on the other side. So the rearranged formula becomes T2 V1 over T1. So let's plug those numbers in. Take 263 times 45, divide by 298. Kelvin, of course, cancels out, and we get our answer in liters. Okay. By the way, whenever you get these answers, a quick check is to see if they match up with the laws that we've seen already. So like in the previous problem, Boyle's law tells us that if our pressure is, if we look at our two balloons, our pressure is increasing. So Boyle's law tells us that our volume should be decreasing, right? Since pressure and volume are inversely proportional. Okay, so notice that the volume that we get is going to be smaller than 125 milliliters, right? Which is what we observed. We had gotten a volume of 88 milliliters, which is smaller than 125. Likewise, in this problem, our temperature is decreasing, which tells us then that according to Charles's law, if temperature is decreasing, then our volume should also decrease, and we'll get an answer lower than 45. Okay, and that's the case here. We get an answer of 39.7, which is lower than 45, and that's a great way to check to make sure we probably set up the problem correctly. Okay, so that's a quick check for your work there. All right, So here's one more gas law problem. I'm going to skip on ahead in the interest of time, but feel free to try this one out on your own. And and obviously I'll have the answer up here. If you do get stuck, here's a little hint for you. Notice that you've got a gas cylinder. They give you a volume, they give you a pressure, they give you a temperature. Note that your temperature is in degrees Celsius. You may want to convert that to Kelvin. Okay. They don't give you the number of moles, so you can use this information and PV is equal to nRT to figure out how many moles of helium you've got in your cylinder. They then ask you how many balloons can you fill, and they give you information about the balloons. They give you a volume, they give you a pressure in torr, which you might want to convert to atmospheres, and a temperature, which again you might want to convert to Kelvin. So again, notice they don't give you moles. So you could break this down to two problems. You've got your cylinder of helium, okay, and you can figure out how many moles are present, how many moles of helium are present in that cylinder. Likewise, they give you information about balloons. You can figure out how many moles are present in each balloon, knowing that each balloon has a volume of 5 liters. And then the question asks, well, how many balloons can you fill up from this cylinder? You basically take your moles of helium from your cylinder and divide by your moles of helium per balloon. Okay, so again, I'm going to skip on ahead and let you solve that yourself. So feel free to pause this if you want to try this out yourself. Okay, so now all of the examples we've done so far have involved a single gas, right? We've only ever dealt with one gas at a time. What do we do with mixtures of gases? Now, mixtures of gases are something we have to take into account because, well, we deal with them all the time. Air is a mixture of gases, right? We're going to do problems in a little bit that involve what we call a wet gas, where we have water vapor mixed in with our gases, and we have to take into account, that water vapor gas is going to affect our sample, right? So what do we do, or how do we treat a mixture of gas? Well, let's think about those variables, pressure, volume, temperature, number of moles, when it comes to a mixture of gases. When it comes to the volume of a mixture of gases, well, our volume stays constant, right? Because our gases are going to be in the same container, right? And they're going to have a volume that matches that container. Likewise, the temperature is going to stay constant. Each gas in your mixture is at the same temperature because the whole sample is at that same temperature. Okay, moles are moles, right? You've got however many moles you have of your gas in there, and that's that. So what about pressure? How does the pressure of your individual gases contribute to your total pressure of your mixture? Okay, and that's the key thing we want to look at here. Right? And that brings us to Dalton's law of partial pressures. Dalton's law of partial pressures states that the total pressure of a mixture of gases is the sum of its parts. Okay, now usually when I tell students that, their immediate reaction is, wait, that's it? Like, the guy got a law named after him for that? But yes, that's basically it. If you have a mixture of gases and you have partial pressures for each of them, the total pressure is the sum of those two parts, or however many parts of gas you have. So for example, here we have a tank that's a mixture of helium and argon. If the pressure of just the helium is 2 atmospheres and the pressure of just the argon is 4 atmospheres, well, the total pressure is 6 atmospheres. That's basically it. All right. The reason for this is since our temperature and volume are constant, your pressure is directly proportional to your number of moles. All right, so since the total number of moles is the sum of the moles, likewise the total pressure is going to be the sum of the pressure. All right, so let's try a problem out that way. Now, when it comes to these Dalton law problems, be very careful if you are given the total pressure or if you're being asked for the total pressure, because you're either going to add things up or subtract them accordingly. Okay, so watch out for that. Also make sure that your units match up. It's really hard to add or subtract things if they're in different units. Okay, so you may have to convert things accordingly. So let's see this example here. A scuba tank contains oxygen with a pressure of 0.45 atmospheres and helium at a pressure of 855 torr. What is the total pressure in torr in the tank? Okay, so everything's in the same tank, so you know that volume and temperature are staying constant. We're just worrying about pressure here. So we're being asked for the total pressure, which is the sum of the pressure of oxygen and helium. So we just have to add up our two numbers. However, again, notice that your units are not the same. All right, your pressure of oxygens in atmospheres, your pressure of heliums in torr. Since we want our final answer in torr as well, I would recommend changing or converting your atmospheres into torr. So we take our 0.45 atmospheres, multiply by 760 millimeters per atmosphere, and we get our answer at 342 millimeters of mercury, okay, or 342 torr, it's the same thing. Okay, so then we take that number and we add it to our pressure of helium, and we get our total. So 342 plus 855 gives us a total pressure of 1,197. Okay, that's it. Okay, so let's try another problem out. Now, this one is interesting because this question gives us a total pressure. We're told that the mixture of helium and oxygen in this tank has a total pressure of 8 atmospheres. Okay, now you're told that the oxygen in the mixture has a pressure of 1,280 torr, and you're asked what is the partial pressure of the helium. Okay, now notice that all your answer choices, this is done as a multiple choice question, and all of your answer choices are in torr. So I recommend dealing only with torr, so you might want to convert your atmospheres here into torr before you try this problem out. Okay, so once again, 1 atmosphere is 760 torr, so take 760 and multiply it by 8 to figure out the pressure in torr, the total pressure. Okay, so now ask yourself, do I take that total pressure, do I add or subtract my 1,280? Okay, so remember, we're trying to get part of the total, so we want to subtract from the total. Okay, so first of all, our total pressure is 6,080 torr, and from that, we're going to subtract our 1,280. Okay, and so we get 4,800 torr. That should be our answer. Okay, so that was C, answer C in the multiple choice problem. Okay, I vaguely alluded to the concept of a wet gas earlier. Basically, it's when a common way to collect gases in chemical reactions is to have just to bubble it through water and collect it in an inverted graduated cylinder. I know I'm using a test tube here, but actually the better way to do this is to use a graduated cylinder, because that lets you quickly measure the volume of gas, right? This is just a very convenient way to collect gases from a reaction, right? Because you don't have to worry. The water helps you, avoid, you can tell if you've got any leaks, basically. So you can make sure you're trapping all of your gas here and getting the total volume very, very accurately. Okay, the problem though is, of course, since this gas is bubbling through water, it's going to pick up water vapor, and that's present in this trapped cylinder, right? Due to the vapor pressure of water, you've got to take into account that not only is your gas from your reaction over here, but you also have water vapor mixed in there. So when you look at the pressure of this sample, you're not looking at the pressure of just your dry gas, you're looking at the pressure of the water vapor as well. Okay, and so you have to take that into account when you're doing any calculations involving that sample of gas. So let's try a problem out involving that. We have 352 milliliters of gaseous nitrogen that we're collecting in a flask at a temperature of 24 degrees Celsius. Now, we're told that the pressure inside the flask is 742 torr. Okay, but remember, that's the pressure of your wet nitrogen. It's nitrogen with water vapor mixed in there. The question asks, what is the mass of nitrogen that we're collecting? Okay, so we have the volume of the nitrogen. We may want to convert that to liters. We have the temperature of the nitrogen, which we may want to convert into Kelvin. In order to figure out the mass, we probably need number of moles. So if we had the pressure of the nitrogen, we could then use our ideal gas law to solve for moles. The problem here is that this is not the pressure of nitrogen. This is the pressure of nitrogen and water. So we need the pressure of just the nitrogen. Now we're told that at 24 degrees Celsius, the vapor pressure of water happens to be 22.4 torr. So that's going to help us in our first step. Let's break this down into 3 steps. We first want to get the pressure of our dry nitrogen. We're going to use Dalton's law for that. We're next going to try and get the moles of nitrogen. We'd use the ideal gas law for that. And then finally, if we have the moles of nitrogen, we can convert to grams using our periodic table. Just look up the molar mass of nitrogen using your periodic table and convert accordingly. Okay, so you'd have to multiply by molar mass to get moles to cancel out and leave your answer in grams. Okay, so we learned that in the last chapter. So yeah, go ahead and feel free to pause this video and try this out, and I'll go over the answer in a little bit. Okay, so that first step's pretty easy, right? We take 742 torr, we subtract 22.4 torr, and we get the answer of 719.6 torr. This is the pressure of just our dry nitrogen. Now, since we want to use atmospheres for our ideal gas law, you'd accordingly convert that into atmospheres, right? So convert to atmospheres. Likewise, you want your volume in liters, you want your temperature in Kelvin. So if you take PV is equal to nRT, we can rearrange that to solve for N, right? N is equal to PV over RT, if we've rearranged that formula properly. Okay, so you then plug in those numbers. Okay, your units should cancel out with the units of R. I've kind of left out the units of R here, but everything would cancel out properly if you had them in there. And you get moles of nitrogen. All right, which is great, but we're not done with the problem yet. The question didn't want the answer in moles, it wants the answer in grams. So we look up nitrogen in our periodic table. Nitrogen, the element, is 14 grams per mole, which means N2 molecules are 28 grams per mole. And so we multiply those two numbers. Moles cancels out, right? And we get our answer in grams. All right, that's it. So go ahead and try out some of these practice problems, for homework. This chapter has an exam after it, so there will be a practice quiz on this chapter available on Blackboard. So feel free to try that out, and of course, don't forget to go over your quizzes from chapter 7 and 8. So you can try and get these questions that you got wrong on those quizzes, get them right on the exam. Okay, and as always, if you have any questions, please let me know, and good luck.